Okay, so the title of my talk is Crossing the Valley of Death via a chips-enabled renaissance in co-design. Now, crossing the Valley of Death is it's kind of like a goal for the U.S. CHIPS Act, right? I'll have a graphic later that'll do a better job of explaining that. But before I do that, I think most of you know me for my engagement at HPC, the Exascale Computing Project. I wanted to share a little bit of my history. So a little over 33 years ago, I was hired into Sandia National Labs, and I was doing work in an experimental shock physics group. So the problem I was looking at and the opportunity I was given was to develop a pulse laser holography system to capture impact-generated fragments. And this is a quick animation, but basically a 6-millimeter steel ball was moving at 4.5 kilometers per second, and 20 microseconds after impact, the laser was pulsed, and that captured this image from an open shutter camera, which shows on the left-hand side an impact flash, and on the right-hand side, it froze the motion of impact-generated fragments. Now, the whole goal of this was to collect three-dimensional data for the shock physics hydrocodes that Sandia Labs was developing at the time, and in particular to help develop fragmentation models for understanding material response, how materials break up under high stress. And I'll confess, this particular image was not one that captured a good hologram, because that impact flash on the left-hand side created a lot of noise on the holographic plates. So in future tests, this whole enclosure was in a box that helped protect the photographic film. But I was also prompted to share this because of the images that David showed yesterday of the kinds of image analysis his company was doing. And I'll note that the optical engineers at Sandia got us down to under 10 microns of resolution, which was like a factor of 5 better than our codes could simulate. And the real challenge here was a data analysis problem. It was a manual process to mount a microscope on a stage, measure the positions of every fragment, and characterize maybe the size of a fragment. And that was all manual, at least at that point in time 30 years ago. I think we should revisit that capability now with advanced image processing technologies to help automate that whole data acquisition process. But this was a prior life. My movement from experimental shock physics to high-performance computing happened because the largest user of the hydrocodes within Sandia National Labs were actually they used probably over 70% of the cycles at Sandia at that point in time. So that was my entry into high-performance computing. All right, so this is the outline of my talk. I'm going to cover 4 different topics, starting with the U.S. CHIPS and Science Act. Shortly after joining PNNL, and I joined there about 6 years ago in April of 2018. Shortly after that, I was asked to participate in this BOE Office of Science Basic Research Needs for Microelectronics workshop. And my focus was really on, the identification of co-design activities for the post-exascale era, and how it would impact microelectronics from processing, memory, interconnection network perspectives. But we also went into materials science needs and and that then covered things like power electronics for the power grid. That activity led to my participation in the Semiconductor Research Corporation's decadal plan, a whole series of workshops that covered different aspects of microelectronics. One of the key seismic shifts that was identified in this report and the workshop series was the need to really take a serious look at energy efficient computing, and this is much more than what we've traditionally been talking about. I mean, we're thinking that, well, the recommendation from the report was we need to be thinking like a million times improvement in energy efficiency. And why that is because if we don't have that level of performance improvement, then we'll never get beyond exascale to zettascale, yotta-scale, and beyond. So you're essentially your energy or your power input into our supercomputing centers will be more or less constrained. And this plot on the right-hand side is from the report. It's an interesting plot. Let me explain what we're seeing. This is a plot of world's energy production and compute energy in terms of joules per year. Yellow curve, energy production of all types, and the green curve, the trends and the projection for compute energy and how it evolves over time. And the scale on the bottom is every 10 years from 2010 to 2050. And the point here is the amount of energy consumption and computing is getting much closer to the total energy production of the world. And at some point, computing performance will stall because there's just not enough energy available. So to get more progress in future progress in computing performance, we need to have real serious improvements in energy, computing energy efficiency. This is part of what drives investments in non-von Neumann architectures, neuromorphic computing, quantum computing, analog computing, a whole range of other approaches that are now the subject of a lot of research investment. See, about a year and a half ago, within the U.S. government, there's the President's Council of Advisors on Science and Technology, and they listed a set of research recommendations directed towards the Secretary of Commerce. And Gina Raimondo is leading the NIST investment in the CHIPS Act. Most of us know about the $39 billion that involves manufacturing incentives to bring fabrication plants onshore, and then they're matched with a bunch of tax incentives. But there's also an $11 billion investment in R&D in microelectronics. And in my next couple of slides, I'll outline a couple of those program elements. But what's interesting here is the R&D to address a number of different areas. I'm most interested in this energy efficient computing and domain specific accelerators. But Duncan, you'll note that one of these is also semiconductor and system security. So, and there are other technology investment areas that we're also interested in, like design automation tools and methods, and the advanced packaging. So this is a photograph from the signing of the CHIPS and Science Act. Here in words are the budget allocations within the U.S. Department of Commerce. Beyond that, the Department of Defense also has a $2 billion investment for microelectronics hubs and technology commons. There was authorization within this act for the U.S. Department of Energy to have a comparable scale of a program, and so planning at least was started within DOE to have a comparable level of activity. Unfortunately, the U.S. Congress has not since made appropriations, so that means the funding is not there, you have DOE has a green light to make plans, but without funding, we can't really execute on plans. So, but back to NIST, they establish the CHIPS R&D program office, and I'll outline two of the main elements. One is called the National Semiconductor Technology Center, and its goal is really to address this challenge, to provide hardware prototyping and testing of advanced microelectronic concepts. Now, that testing and prototyping is all kinds of things, from advanced materials, advanced manufacturing processes. The part I'm most interested in, of course, is advanced computing concepts. Again, those domain specialized accelerators that we may have ideas to put on the table. And the other challenge that NSTC should address is access to the test facilities, piloting capabilities, the design tools, the ability to create test hardware and make hardware an R&D topic in and of itself. Another major area of investment is the National Advanced Packaging and Manufacturing Program. Bob gave a good overview of the differences between 2.5D packaging and 3D packaging. Much of this investment goes towards 3D heterogeneous integrations, and that means then the stacking of chiplets or dielets. The text in here is provided from a presentation from Subbu Iyer. At this point in time, in 2016, he was a professor at UCLA. He's now the director of the NAPMP, National Advanced Packaging Manufacturing Program. So he makes this point, the distinction between chiplets and dielets, which is important to keep in mind. But ultimately, what we're talking about are the building blocks that support prototyping and testing of different types of heterogeneous computing concepts. So I'll come back to that. All right, crossing the valley of death. This is a graphic that I wanted to share. On the left-hand side of this plot is fundamental research. This is where the Department of Energy, DARPA, and NSF make investments. Then we do well with fundamental R&D in microelectronics and advanced computing. The key question is, how do those technologies transition to the private sector? How do they become real commercial products? And this graphic from NIST shows, and the CHIPS R&D program shows where NSTC shows up, the Advanced Packaging Manufacturing Program, those DoD Commons, microelectronics commons hubs. There's another element called Manufacturing USA. It's meant to be a microelectronic manufacturing institute that again helps transition concepts into proof of concept, and then technology demonstrators that could transition to the private sector. I'll argue that the DOE, in addition to investing in fundamental research through our investments in programs like Path Forward for the Exascale Computing Project, have also occupied some of this middle ground where those architecture R&D investments have funded the opportunity for the national labs to participate in co-design collaborations with our vendor partners and really deploy first-of-a-kind systems that may have had a price tag that was too high for just the commercial world to buy, but for mission-driven deployments, first-of-a-kind system will make sense for the government. All right, let me switch gears. I'm going to do this very quickly because I've spoken previously on the Data Model Convergence Initiative. That's an LDRD initiative at PNNL that I've led for the last 5 years. So my use case is converged applications that really integrate scientific simulations with scientific AI and data analytics, then use that as a driver for the development of advanced concepts for heterogeneous computing, in the development of the system software stack that maps these converged applications to the heterogeneous computing capabilities. And I double-checked all of these links are active, they're current, so you can look at these things at your leisure. So this is kind of a picture of our view of the technology stack for heterogeneous computing. And at the top, we have these converged applications for scientific modeling and simulation, AI, and data analytics. When we go into two MLIR-based compiler frameworks. One is called Comet, and it's meant to map, again, the patterns and compute capabilities from these converged applications through MLIR lowering to different hardware processor design targets. We've also been investing in software-defined architectures, which is our front end for high-level synthesis tools to help us define what the hardware can look like for customized or specialized concepts for hardware solutions. Another example of that from the commercial world is Vitus, which is the high-level synthesis entry to Xilinx FPGAs. We've also been developing a runtime to help coordinate this mapping of application workloads to the different processor types that are available for our test beds. Just a little bit of detail on the Comet domain-specific compiler. Again, we're looking at mapping a domain-specific language, in this case for tensors, NumPy, SciPy, or Rust-based applications, doing high-level optimizations, low-level optimizations, and then mapping to different heterogeneous processor targets. Here's an example from computational chemistry, where we're looking at how many the tensor operations for our computational chemistry codes that include things like tensor contraction engines can be subject to different levels of optimization or performance improvement. The same can be said for our work on graph analytics, where we can look at decomposing the problem and applying different optimizations for the data movement associated with these graph analytics applications. This is an example using a benchmarking from triangle counting, but our graph applications include things like community detection, influence maximization, other kinds of graph-based applications that are not necessarily a good match to GPUs or CPUs. And that's why this is where we see opportunity for some of these domain-specialized, not just applications, but hardware accelerators that are designed to tackle some of these graph analytics computing patterns. This is then on the hardware side, the soda synthesizer. The key here is these are capabilities that, in a sense, are capabilities that are also available in the commercial world with tools like Synopsys and Cadence or Siemens tools. But the difference is these are designed for more of a research implementation, and they don't require a 50-person team. Now we're not designing production grade hardware, but I think there's now going to be a new role for hardware design that's targeting research as opposed to product, and that's something we're not used to. I'll come back to that in my closing comments. But ultimately, the goal for this high-level synthesis tool is to take as a front-end input from different types of application definitions, build up a library of templates and pre-built components, go into a back-end that's based on the P&A Bamboo high-level synthesis tool. The output is Verilog, and that can either be implemented directly in FPGAs, or coarse-grained reconfigurable arrays, as a way of testing the hardware designs and concepts. Or they can go into other lower-level open-source hardware design tools that have been funded by the DARPA Microelectronics Technology Office. Here's an example of the hardware design tools being applied to the Linnet convolutional neural network architecture. With no optimization, you have, these are actually images of how much area is consumed by an ASIC or each step of the CNN architecture. In our optimized flow, we'll use more area, but the key thing is that these optimized accelerators actually run faster. So I'll come back to the ecosystem. So this is actually my connection, I think, to the multi-core world and the interest in open sourcing. So our tools are all open sourced. The work on our hardware design side, our hardware design capabilities actually can interface to an ecosystem of hardware design capabilities. Some of them have also been developed by DARPA investments. Some of them are now able to interface to the commercial ASIC logic design tools. But that being said, there's still significant challenges. There's much more work to be done if we're going to get our SOTA hardware design capability to be up to production grade quality. But we'll have to worry about dealing with IP considerations. And we really need to have a target, i.e. the investment by Department of Commerce for their hardware prototyping infrastructure. But that's something we're paying attention to as an opportunity for DOE to have some impact. There's a tool called OpenFPGA that DARPA has funded. We've also been developing something called OpenCGRA, coarse-grained reconfigurable arrays, to help prototype concepts. Ultimately, there are other factors that are required, that NIST investment in advanced packaging. I noted that John Schauf will be here next year. I'm sure he'll talk about standards for chiplet interfaces, which then is part of this marketplace where with a portfolio of chiplets that are commercial, that have standardized interface, you can actually think about composing hardware to build up heterogeneous processor concepts. Now, that's the hardware side of composability that needs to be supported by the system software and runtimes for composability. And then I'll talk about CXL in a moment. At least the sharing capability within CXL might provide some of the memory interface requirements that also enable heterogeneous computing. All right, these are all of a listing, maybe I'll call it a partial listing of the open source software repositories. Some of these are within PNNL, like SOTA, Opt, and Comet. PNA and Bamboo is from Politecnico de Milano. Open Road is from UC San Diego, Andrew Kong's project. Silicon Compiler is from Zero ASIC, a former DARPA program manager that funded some of our work started up Zero ASIC, and this is the name of his open source compiler tool, but it's something that SOTA can interface to directly. And then there are other capabilities of when we interface to Open Road that then has a path to test chip tape outs at foundries like Global Foundries or Skywater. But that's the hardware side of things. This is in the slides I've uploaded, a bunch of our references. I will point out that this SOTA toolchain paper was published in IEEE Micro And a month ago, we were informed that it was voted best paper of 2022. So we're very happy to see that. Shifting to hardware software co-design, some of the activities we're also working on with support from the DOE Office of Science. PNNL leads a project called Advanced Memory to support AI for science. Andres Marquez is our PI. His counterpart at Micron is Tony Brewer. Just some of the concepts that are investigated here include the use of fabric-attached memory, leveraging the Compute Express Link or CXL standard. We're looking at how that CXL interface can support modules that have compute near memory processing capabilities, along with DRAM. You can build up very large systems of memory modules. This is showing where you might have a switch fabric interface based on CXL. If you have multiple tiers and you really had enough money, you could populate up to 4,000 memory modules and get to over petabyte, multiple petabytes of main memory in terms of memory pools. Now, similar to what Bob was discussing in his supernode concept, there's some questions about how large a memory pool is addressable, when you'll run into scaling limits that require some of the co-design collaboration that we're working with Micron on for this project. We're looking at application drivers from things like graph algorithms, sparse neural networks, different AI kernels, and this is a project that is now in its third year. We're starting to expand to work with our colleagues at the other labs, including Adolphi's team at Brookhaven. This is just a quick snapshot of the different thrusts that we have in this project. High-level synthesis, performance analysis, machine learning, and scale-up. We're all part of the Data Model Convergence Initiative. Some of the new activities are the scale-out activity for larger runtimes and larger scale runtimes. And then a new thrust, Duncan here, on data privacy and security. This is a slide contributed by Tony Brewer, and he gave a keynote talk at our IA3 irregular architecture applications, architectures, and algorithms, or I have it backwards, I'm sure, but that's a link to the website for that workshop. You'll see this graphic has a little bit of a difference in that attached to the CXL low latency fabric are not just CPU nodes, but also GPU nodes that may have their own proprietary interconnection network and special purpose processors, things that we're designing with SOTA. Another thing to note is that the data formats for this memory would be the data formats that you need for computing rather than data formats for storage. So when we talk about zero-copy data sharing, we're thinking about a very large memory space that could be directly accessed by processors, heterogeneous processors, and not require data transformations as you might have to do right now when you address very large data stores. And then digging into details on the near-memory compute functionality. Again, I can talk about this now because Tony shared this at supercomputing, but even within this memory module, the idea is that you have a CXL memory controller. You may have hard RISC-V cores, the definition of a couple other engines for data movement, for threading, for streaming. These are examples of IP blocks that could be implemented as dilets or chiplets. And again, this is the kind of exploration that I think we need to have hardware prototyping available to help us explore. But that's definitely the kind of capability that we're looking for in the future. Coming to the end here, Here's another new initiative at PNNL called At Scale. And the idea behind this, I should acknowledge the chief scientist for this initiative is Mitra Tahiri, who's from Johns Hopkins University, but she shares a joint appointment with PNNL. And our technical lead is from the material science community at PNNL, Dan. And the goal of this is to look at 4 different thrusts and their devices, theory and simulation, operando synthesis and materials characterization, and then low latency reasoning and control. These are the 4 technical thrusts. And then we have some science drivers that are used to, again, define co-design requirements, application drivers that then drive co-design design space explorations amongst the other 4 thrusts. And the next slide will dig into the low latency reasoning, which is led by Antonino Someo. And ultimately the point here is that we're finding that there's an opportunity for customized hardware designs that will outperform CPU or GPU implementations. No surprise, but especially when you're talking about low latency requirements, in this case for in situ processing that's very close to the instrumentation or the tools that are used for material synthesis. One last shout out to Microsoft. We just started earlier this year a project that includes Microsoft and Micron and a number of academic partners and Lawrence Berkeley's National Lab. And in a nutshell, the key point behind this Accelerate project is to also bridge the Valley of Death, but start with a computational chemistry application that was developed with funding under the Exascale Computing Project, get it transitioned to Microsoft Azure to provide computational chemistry as a service. And the thinking here is that right now, this investment in Northwest Chem EX for Exascale Northwest Chem computational chemistry package is available to anyone that can get access to the Exascale platforms within DOE. But that's not a large population of users. And so the thinking behind this is to ensure that that computational chemistry capability can be available to a much larger population of users through Microsoft Azure. We are also still looking at advanced memory opportunities, and that's why we're working with Micron as well, along with their counterparts at Microsoft Azure, to think about how maybe the opportunities for very large pools of memory can help us refactor and revisit how these computational chemistry applications are deployed and ported to the cloud computing environments. And then, of course, through Microsoft and the connection to AI, there are lots of opportunities for applying AI and integrating it closely with scientific simulation like computational chemistry. All right, just some closing thoughts. The impact of Moore's Law on HPC. I basically started my career in HPC when we were seeing Moore's Law bring about the end of Cray vector supercomputers. And really, at that point in time, get us to the position where developing custom processors, custom memory, custom systems took too long, and performance would be overcome by just the natural progression of the commodity computing world when we were benefiting from Moore's Law and Dennard scaling. But Moore's Law actually had another benefit, which meant we didn't really need to have co-design as we're now thinking about it. What you had was a pretty stable technology stack, and as long as you were developing microelectronics technologies, computing technologies, material science, you had a target for where your advances in your technology area might be used by other engineers and scientists that were working in elements of the stack above or below you. And for 30 plus years, that was really the benefit of NAPMP. This is that graphic from the Basic Research Needs for Microelectronics workshop. And one of the things that this is meant to convey is that these technology areas no longer necessarily line up in a clean stack. And especially when you're thinking about new materials for neuromorphic computing or new memory technologies, an advance in the material space can result in changes in algorithms and changes in how we envision using that advance and when it's deployed in a new concept for a processor. So ultimately, this is really this notion that we're seeing definitely in quantum computing, that the interfaces and boundaries in this post-Moore's stack are fluid. And in fact, the definition of those interfaces, I would argue, is really one of the goals of co-design when you're working in a new space like this. All right, impact of the CHIPS Act. So again, greatly lowered costs of hardware prototypes is a goal of the National Semiconductor Technology Center, or the National Center for Advanced Semiconductor Technology. That's the name of the public-private partnership, NatCAST. That's the name of the program element. So that goal combined with the goal from the packaging investments in 3D heterogeneous integration will lower the cost for hardware prototyping. And from a computing perspective, I think it will lead to this kind of balance where we haven't had that balance in software R&D versus hardware R&D, at least for the last 30 years. And so we have to get away from the idea that creating a hardware prototype requires $100 million. Just imagine what you could do, what universities could do, small companies can do, if the cost of taping out a hardware prototype is $100K, even $1 million. I mean, the barrier for an entry could be very much lower. And that's the goal of the CHIPS Act in terms of crossing the valley of death, getting advanced concepts transitioned to product. It's all about democratizing innovation so that you don't have to own your own fab or be one of the largest players to access and develop hardware concepts. And then what we do with the hardware concepts is test them with software. So if we've done our homework with co-design, you aren't just taping out a prototype of a domain specialized accelerator. You're sitting there ready with your application and algorithm software, maybe a research version of your compiler tool chain and runtime system so that you can immediately move to quantifying the performance in terms of energy efficiency, in terms of cybersecurity, things that are not easy to do in a simulator or even an emulation platform. These are things that you can now do with test hardware. The other thing I'll point out is if you have open source design tools and you're combining them with a prototyping infrastructure, maybe there are other new opportunities. Like right now, new hardware requires you have scale. If you're going to design a new processor, you need to have the volume of production like an iPhone to make it worthwhile. And there are a lot of use cases that are currently unmet. Where's Will Camp? You might benefit from having an ASIC that you can tape out where you only need to have 1,000, right? Yeah. So So the idea of small volume production grade hardware, it could be game changing, right? And in fact, it might change our whole view of computing. I think we had some discussion earlier about customization and its role, and this could change the rules of the game, where customization might actually be something we could all benefit from. Let's see. And I'll just note that within at scale, we're not looking for test hardware, tape out. At the present time, our targets are FPGAs or CGRAs. But in the future, if energy efficiency or cybersecurity were important, that might be the place where you want to tape out an ASIC and convert designs to real hardware. And with that, I'll stop and take questions.